In 1976, a 21-year-old student at Princeton University designed a working atomic bomb for a term paper, forcing the federal government to immediately classify his homework. His design relied entirely on publicly available textbooks, proving that the theoretical recipe for the most destructive weapon in history is open to anyone. Yet, despite the simplicity of the mathematics, a single scarce element prevents amateur groups from turning these blueprints into fireballs: 3 neutrons. Since basic blueprints are accessible, our safety depends on the extraordinary difficulty of separating isotopes that differ by a tiny fraction of mass. The story of this physical barrier began in the cold December of 1938 in a Berlin laboratory. A German chemist named Otto Hahn fired neutrons at uranium atoms, expecting to create a heavier element but detecting barium in his samples. In Sweden, his exiled colleague Lise Meitner calculated that the split fragments weighed slightly less than the original uranium atom. Using the formula where energy equals mass times the speed of light squared, she realized this missing mass had converted into a massive burst of energy. This discovery sparked immediate fear that a chain reaction could release millions of times more energy than chemical explosives. By 1939, Albert Einstein signed a warning letter to President Franklin Roosevelt, urging him to initiate a research program before Germany could exploit this discovery. The American response was the Manhattan Project, a massive enterprise that eventually cost $2 billion. The project grew into a secret industrial empire, employing over 125,000 workers across 3 custom-built cities. Thousands of these workers performed repetitive tasks behind barbed wire, completely unaware of their true mission. In Tennessee, they built Oak Ridge, a secret town of 75,000 people that did not appear on any map. In Washington state, they built Hanford, a massive reactor complex next to the Columbia River to produce plutonium. In New Mexico, they established Los Alamos, a remote laboratory where the world's top minds gathered under military guard. At the secret facility in Oak Ridge, workers faced an isotope separation problem that defied standard chemical sorting. Natural uranium ore contains 99.3% uranium-238, leaving only a tiny fraction of the fissile uranium-235. Because these isotopes share the same chemical properties, they differ only by a tiny mass of 3 neutrons. To sort them, engineers pumped corrosive uranium hexafluoride gas through thousands of porous nickel barriers. The lighter uranium-235 molecules passed through the microscopic holes slightly faster than the heavier isotope. Repeating this filtration process 1,400 times in a continuous loop slowly enriched the gas to weapon-grade purity. The K-25 building at Oak Ridge stretched for half a mile in a giant U-shape, housing thousands of stages of diffusion equipment. Workers rode bicycles down the long corridors just to monitor the valves. The enrichment facility at Oak Ridge consumed more electricity than New York City to sort atoms that are nearly identical. Slow uranium enrichment forced the project to pursue a parallel path using man-made plutonium. At Hanford, giant reactors bombarded uranium-238 with neutrons to create plutonium-239. Since plutonium is a distinct chemical element, engineers could separate it from uranium using liquid chemical extraction. This extraction left behind millions of gallons of highly radioactive waste that remains hazardous today. Detonating the bomb requires forcing a subcritical mass of fissile material into a supercritical state. If this assembly happens too slowly, the reaction begins prematurely, causing a weak fizzle, a dud. For the uranium bomb, engineers built a gun-type mechanism that shot one subcritical block of uranium-235 into another inside a steel barrel. This cannon design was so reliable they dropped it on Hiroshima without testing it first. The plutonium bomb demanded a far more complex approach. Plutonium undergoes high spontaneous fission, meaning a gun design would predetonate and fizzle. To trigger plutonium, engineers squeezed a solid sphere of the metal into a superdense mass using a symmetrical inward blast. They surrounded the plutonium core with 32 shaped explosive lenses that converted an outward explosion into a spherical inward shockwave. These lenses had to be cast without a single air bubble, as any pocket of air would disrupt the detonation wave and ruin the compression. The detonators had to fire within a fraction of a microsecond of each other to prevent the core from squirting out the side. On July 16, 1945, the project tested this implosion design in the New Mexico desert. The heat of the explosion was so extreme that it momentarily reached temperatures hotter than the center of the sun, vaporizing the steel tower. The blast was so intense that a blind woman named Georgia Green, riding in a car 120 miles away, felt the flash of light. This explosion fused the desert sand into a green glass known as trinitite. Watching the massive cloud rise, Robert Oppenheimer recalled a famous line of Hindu scripture about becoming death, the destroyer of worlds. Today, 9 nations possess these weapons of mass destruction, and the engineering blueprints are widely available. The physics is taught in colleges worldwide, leaving industrial enrichment as the only barrier to entry. Operating thousands of high-speed centrifuges requires specialized carbon fiber rotors, precision manufacturing, and a massive electrical grid. If civilization collapsed, survivors could read the textbooks but would lack the industrial capacity to build a bomb. They would have to rebuild the massive factories of Oak Ridge and Hanford from the ground up. The Princeton student proved that the blueprints can never be locked away, yet our survival remains protected by the difficulty of sorting atoms that differ by just 3 neutrons. Which part of this industrial process do you think is the hardest to replicate?